Okay, so we're going to get started with what could potentially be the final video, at least in the transmitter series. And that's, so let's just summarize where we got up to in the last video. So we completed the signal processor. We've confirmed that the quadrature sampling encoder works fine. We've got the combiner after the quadrature sampling encoder, and then we've tapped off the output and had a look at that output, and it looks pretty good. So what we're going to do in this video is three major components. The bandpass filter straight after the quadrature sampling encoder. So we'll get that installed. We'll have a look at the output after the bandpass filter to confirm that it still looks good. And then finally we'll add the amplifier, PA, and LPF, and then we'll be ready to do some transmission tests. So anyway, let me get started on the bandpass filter, and we'll come right back. So if you've seen any of my videos, you'll probably have seen this double-tuned bandpass filter before. And just to be clear, this isn't my creation. I did borrow this off the QRP Labs bandpass filter implementation. I thought it was a great performing bandpass filter. But anyway, so just to sort of walk through the circuit, you have a pair of transformers, one on input, one on output, and then a pair of variable capacitors that you use to adjust the signature of the bandpass filter, and then you have a couple of caps here that forms a resonance circuit between the input transformer and the output transformer, and you've got a bandpass filter on the output. So anyway, I've made a few little boards of this just to ease the incorporating it into the circuit. Let's move on to that now and have a look at those little boards. Okay, so here's the bandpass filter board that I've created here. Here's an unpopulated board down the bottom. So the variable cap and the transformers go on the top, and then the rest of the caps are SMD 1206 SMD caps on the bottom here. So this BPF is tuned to 10.1 megahertz, which is what we were using before. I will have to change that when I want to transmit, of course, because you can't transmit SSB phone on 30 meters. That's not allowed. But so anyway, I will change this later on. And I did have a viewer question a little while ago on how to derive these values. Frankly, I don't know how to, other than the kind of the resonance between the inductor on the input transformer and output transformer and the caps as a starting point. But I have got some techniques to do this experimentally. If anyone's interested in that, just let me know in the comments, and maybe I'll do a separate video on at least how I do it, derive these values experimentally. Anyway, why don't we, let's get this on the spectrum analyzer, or at least have a look at the signature of the BPF, and then we can get it incorporated in the circuit. Okay, so I've got the bandpass filter hooked up to the spectrum analyzer. Let's just go up and have a look at the signature there. So I've currently got it on the peak. Let me just pan up a little bit. And you can see that's around about 10.1 megahertz, and then either side we have about 9.7 megahertz all the way to 10.62. So about around about a 1 megahertz bandwidth of the bandpass filter. So anyway, it's in the right spot. So let's get this hooked into the circuit, and we can see the effect. So the test setup is the same as last time. Injecting a 1 kilohertz tone, not mixed in any way, right here. Here's the bandpass filter, which is connected on to just after the combiner right here, and then that's going off to the oscilloscope, and as you can see, that's 50. I've got a 50 ohm terminator right here on the oscilloscope. So we're on upper sideband right now with that 1 kilohertz tone. Let me just get a better view of that so you can see it. Bear with. Okay. And I'll include up here somewhere a comparison with the previous signal, but as you can see, that's a very, let me just stop that. That is a very smooth single tone signal right there. So all those bumps and artifacts that were on top of the signal without the bandpass filter have gone away. But more impressively, I think, if I start to do the two-tone test, so let me go down to 700 and we'll do the 700 and 1900 two-tone test as we did earlier. And I'll stop that. You can see that signature looks far better than before. So, and you know, the bandpass filter isn't improving. You know, it's not doing anything to improve the unwanted sideband suppression or anything like that. But what it is doing is getting rid of those higher frequency harmonics, the 20 megahertz, 30 megahertz, and 40 megahertz artifacts that we saw before. And in fact, let's go over to the spectrum analyzer, and we'll have a look at the broader band harmonics that are being output here. Okay, so I've got the output of the just after the bandpass filter going into the spectrum analyzer. And as you can see, well, you can't actually see that. Let me go to the peak. So here's our peak here at 10.1 megahertz, the fundamental. But all those other peaks that you saw earlier, and I include a little video from earlier. Let's get that enameled wire out the way. It's annoying me. All those other peaks have gone. So we've got this peak here, which is at 30 megahertz, but you can see it's way down, 55 dBs or so down from the fundamental frequency. So all those harmonics at 20, 30, and 40 have all disappeared, and that's what's responsible for the output signal looking so much better. Now let's have a quick look now at the close-in harmonics around the signal. Now the bandpass filter is not going to affect those in any way, but I just want to make sure that it hasn't unduly affected them. Anyway, so let's have a look at that now. So here's the output, and you can see it has a very similar signature to before. So now we have, we're centered around 10.1 megahertz with a span of 15 kilohertz. Here's the upper sideband signal, the carrier, and the suppressed lower sideband signal. Now the signal's come down a little bit. It was minus 20 dBms before. It's now minus 26 dBms. So we've got some loss from that bandpass filter in the midst there. But all in all, a healthy signal. Swap to the lower sideband, and you can see a similar structure there. So anyway, the bandpass filter's installed. It's doing its job. What I need to move on to next is the PA, and let's talk a little bit about that before I get started. So rather than spin my own PA, I think what I'll do is I'll just use this 10-watt PA that I got from QRP Labs that I've used before. So you can see it's mounted to a heat sink here. Now this requires, I believe, around about a volt peak to peak to get this going. So what I'm going to have to do is put a little a preamp straight after the bandpass filter in order to get that drive up a bit, so that I can drive this PA. So I have got a little circuit to do that, and why don't we have a look at that circuit, and then we'll move on to getting it installed. Well, I've disappeared a little bit down a rabbit hole with this amplifier board. So when I first hooked it up, so here's the amplifier switch here, and what I'd thought is you pass 12 volts in to turn the amplifier on, you actually ground it. So that was my mistake. And when I applied 12 volts, I blew this P-type FET here. But that was not all. I blew all three of these MOSFETs, these BS170s right here, and potentially this other BS170 here. So this BS170 and this BS170 are used to control the bias voltage to the remaining two. So it's all in pieces at the moment, so I guess I'll change the video a bit and we'll walk through how to repair this. I think what the next thing I'll have to do is remove these. Well, let me just get that here. Remove these two IRF 510s underneath here. I don't want to blow these two, and then I'll be able to sort of confirm that that this section of the amplifier is working correctly, and that the voltages on the gates of these IRF 510s are correct. So anyway, that's what I'll do. I do need an amplifier working, and like I said, I don't want to kind of spin my own version here. Let me just change that up. So anyway, we'll come back and I'll test, I'll have these BS170s all installed, and we'll test the output voltages at the gates of these MOSFETs, and hopefully that will be that. Okay, so I've pulled the two FETs out here. I tested them, they seem to be still good. Here they are here, and they are indeed IRF 510s. What I might do though is kind of replace them with some newer IRF 510s. I don't know what else went on while I got the input switch wrong. So anyway, what I'll do is, as I said, get these BS170s back in, and then we'll be able to test that the voltage at the gates of these IRF 510s are correct. Okay, so now I've found that this transistor right here is also bad. So I've pulled that out, and we'll put a fresh one back in, and maybe that will be that. I'm not having much luck here, so this bad transistor blew the new BS170 that I put in here, which is the bias reference, it sets the bias reference. So I've replaced this one. I've checked the bias at the DC bias at the gates of these BS170s here, and that appears to be right, which is around about 2.7 volts. So I'm ready to put these BS170s back in. Okay, so it looks like we're back in action, at least with these BS170s. I checked the bias voltage at the gates of the BS170s, and it was around about 2.7 volts, which is correct. Got them installed back in again, and then I've checked the signal at the gates of the IRF 510s, and that looks good too. So ready to get the IRF 510s back in, and then we can actually see if this amplifier works. Okay, so everything's back together, and it does appear to be working. I had to actually refer back to my own video on this to figure out the settings of the pots and other stuff. So, but anyway, so just to go through the test setup, it's a 12 volt power supply. Here's the output here, and I'm sending the output to a dummy load. And in parallel with that, I've got a connection that goes off to the scope. I'm going to be injecting a 1 volt peak-to-peak signal at 10.1 megahertz. So let's have a look at the result of that on the oscilloscope. Let me just zoom in a little bit there. Yeah, it's all in focus. All right, so let's fire that off. And you can see there, let me hit run stop. So you can see there I'm getting a nice, relatively clean output there. It's not a perfect sine wave, but it is at 10.1 megahertz, and if you have a look there, you can see for a 1 volt peak-to-peak input, I'm getting 43.6 volts peak-to-peak on the output, which is around about 5 watts, which is, I'd like a little bit more for the testing potentially, and I might dial that up a bit, but that's good enough to get started with. Now, obviously, at a 1 volt peak-to-peak input, the output of the Tayloe detector, Tayloe encoder, sorry, is not going to be enough to drive this amplifier by itself. So I'm going to have to build up a little preamplifier circuit to sort of get that 1 volt peak-to-peak signal. And of course, that's going to, introduce its own sort of layer of harmonics and so on and so forth. But that's the fun of this, I guess. So what I'll do next is sort of walk through building up that little preamplifier circuit, and that'll be coming right up. Okay, so in order to build my preamp, first thing I want to know is what the input impedance is of that of the 10 watts, so the QRP Labs amplifier. Now, the instructional manual does say that it is not a 50 ohm input impedance, and the trace here certainly bears that out. I guess I'm seeing anywhere between 220 ohms input impedance all the way up to 450 odd, 440 odd input impedance. So 440 at around about 10 megahertz, all the way down to 220-ish at 16 to 18 megahertz. So what I might do is kind of aim for the middle there, aim for an input impedance of around about 330-ish ohms, and that'll be the output impedance of my little preamp. But anyway, next thing to do is sort of show the preamp itself, and let's take it from there. Okay, so here's the little preamp circuit, and as you can see, it's pretty simple. I've got a 50 ohm resistor on input because the bandpass filter, which is to the left here, does expect to see 50 ohms output. A couple of decoupling caps on input and output, and then this sort of standard configuration of 2N2222, which is going to be an SMD component, appropriately biased, and then there's a T3743 coil on output. I would have liked to have used the input coil that's on the amplifier, but it just didn't work out. Anyway, so let's go and have a look at the board now, and then we'll get it put together. Okay, so here's the board here. Here's where the 2N2222 goes, right in the middle. Here's the RFC coil right here. It's going to be a T3743 with 10 turns on it. And the rest of this is the biasing arrangement, the input and output caps. On the reverse side, it's a double-sided board. On the reverse side, this is where 12 volts goes into the RFC coil. So anyway, I'll get this populated and then we'll be able to do some testing. Okay, so here's the little board all populated and ready to go. And over on the left here, I'm injecting a 10.1 megahertz signal at 120 millivolts peak to peak. And then on the output side, I've got this 390 ohm resistor, which is representing the input impedance of the following stage. So the output impedance of this stage is around about, as we said, needs to be around about 350 to 400 ohms. So let's have a look on the oscilloscope, just panning up there. And as you can see, 10.1 megahertz signal on the output, and around about a peak to peak of 936 millivolts. So, which is around that 1 volt peak to peak, which the amplifier requires. So, all good there. The little preamp board's outputting the around about the right voltage. So we're ready to sort of hook this into the circuit. And so just a reminder, this preamp board will come after the bandpass filter, and in between the bandpass filter and the PA. So anyway, let me get that hooked up and then we'll come back. Okay, so I've got the little preamplifier in the transmit chain now. So from bottom to top, we have the Tayloe encoder here. The output of that goes to the bandpass filter. The output of that goes to the little preamplifier board that we looked at in the last section. And just a note, there is that 50 ohm resistor on the input of that, because that 50 ohm output is what this bandpass filter expects. And one thing I forgot to mention in the last section, the input signal there was 0.12 volt peak to peak. So anyway, let's have a look at the output. Same setup as before. Let me just pan down to the setup so you can see it. So same setup as before. I'm injecting at the moment a 700 hertz tone into the audio input here. I'm using the same setup before. I've got basically 2 channels added together, but they're both set at 700 hertz at the moment. So anyway, I've got the tone coming in here. Tayloe Encoder is doing the mixing, sending the output, and there you can see that output, a very relatively clean output on the oscilloscope there. Let me just change the frequency up to 1 kilohertz. Bear with me. Right, so that's 1 kilohertz left and right. You can see the output is the output frequency is correct. So that's the lower sideband signal, and there's the upper sideband signal, 10.101. You can see I've got some little undulations in the signal, which I didn't have before when I didn't have the preamplifier installed. But as you can see, as I change between upper and lower sideband, the output is as expected. So 10.101 on upper sideband and 10.099 on lower sideband. So anyway, let's do the old two-tone test here. So I've got 700. They're both at 1 kilohertz. Let me move one down to 700 hertz, and I will move the other one up to 1900 hertz. You can see there, very nice. Gonna have to slow that down a little bit. There we go. So you can see there, very nice two-tone signal there, very clean crossing point, a nice sine wave with no distortions. And the difference being now the output is at 1.36 volts peak to peak. If you'll recall, previously the output of the Tayloe encoder was around 0.12 or 120 millivolts peak to peak. So that's that preamplifier introducing about a 10-fold gain in the voltage there. Okay, so let's quickly summarize where we are. So the Tayloe encoder is correctly outputting the signals, upper and lower sideband. That is being fed into the bandpass filter, which is getting rid of all those higher level harmonics. And then the output of that is being sent to the preamplifier that I require, because the output from the bandpass filter is only around about 0.12 of a volt peak to peak, which isn't enough to drive the amplifier. So I'm all ready at this stage to feed the output of the preamp into the following stage, which is the amplifier, and then following that the low pass filter. However, what I'm going to do is I'm going to cut the video here. I want to spend an entire video just on the amplifier and the low pass filter. I will have to spin another board for the low pass filter. So anyway, I hope you enjoyed this video. I hope to get the next video in the series out in the next couple of days, and hope you enjoyed this. More to come.